Here's the script. The universe speaks mathematics. But why? There's something deeply strange hiding inside every equation you've ever seen written on a blackboard. Something that physicists know about, that mathematicians quietly wonder about, but that almost nobody talks about in plain language. And it's this. Nobody actually knows why mathematics works. Not in the deep sense. Not really. We use math every single day to describe reality with breathtaking precision. We point giant telescopes at galaxies billions of light years away and predict where they'll be. We smash subatomic particles together at nearly the speed of light and calculate the odds of what will emerge. And we're right, down to 10 decimal places. We sent a spacecraft called Voyager on a journey past the outer planets using nothing but equations scratched out on paper, and it arrived exactly where the math said it would. But here's the question nobody can fully answer. Why? Why should abstract symbols invented by humans sitting in rooms thinking pure thoughts have anything at all to say about the physical universe? That mystery is what we're going to explore today. And by the end of this, the universe is going to feel both stranger and more wonderful than it did when you started. Stop. Before we go further, think about that for a moment. Mathematics begins in abstraction. A mathematician isn't studying rocks or rivers or stars. They're studying relationships between imaginary objects that don't physically exist, perfect circles with zero thickness, numbers that go on forever, spaces with 11 dimensions. They're playing a kind of elaborate mental chess, following rules they themselves invented, exploring consequences that nobody planned for. And yet, somehow, this game of pure imagination keeps turning out to perfectly describe the real world. That's not supposed to happen. That's the mystery. Richard Feynman, and the question nobody can answer. Richard Feynman, the physicist who helped build the atomic bomb, who won the Nobel Prize for his work in quantum electrodynamics, who could explain black holes to a curious 9-year-old and still satisfy a room full of PhDs, spent a lot of his life being genuinely bothered by this question. Feynman wasn't someone who pretended to have answers he didn't have. In fact, that was one of his defining qualities. He once said that the first step to real knowledge is admitting what you don't know. And on the question of why mathematics describes reality, Feynman was famously, almost defiantly, uncertain. He would sit with his students and say something like this: "I find it quite amazing that it is possible to predict what will happen by mathematics, which is simply following rules which really have nothing to do with the original thing." Read that again slowly. Simply following rules which have nothing to do with the original thing. He wasn't dismissing mathematics. Far from it. Feynman was in awe of mathematics. He described equations as poetry. He said that when you truly understand a physical law, not memorize it, but understand it, it sings to you. He saw beauty in formulas the way a musician hears beauty in a chord progression. But he was also deeply suspicious of anyone who claimed to have solved the deep philosophical puzzle of why math and physics fit together so perfectly. That smelled to him like false certainty. And Feynman had a very low tolerance for false certainty. So we're going to do this the Feynman way. We're going to be honest about what we know, honest about what we don't know, and we're going to let the mystery breathe instead of smothering it with easy answers. The unreasonable effectiveness of mathematics. In 1960, a physicist named Eugene Wigner wrote an essay that has haunted scientists and philosophers ever since. The title alone is enough to stop you cold. The Unreasonable Effectiveness of Mathematics and the Natural Sciences. Wigner's argument was simple but devastating. He pointed out that mathematical structures developed for purely abstract reasons, with no practical application in mind whatsoever, keep showing up as the exact tools needed to describe physical reality. Not approximately, not kind of, exactly. Here's a thought experiment to feel the weight of this. Imagine a musician in ancient Greece. He's sitting by the ocean, not thinking about physics at all, just plucking a lyre and noticing something curious. The shorter the string, the higher the pitch. He starts playing with ratios. He discovers that a string exactly half the length produces a note that sounds harmonious, what we now call an octave. He keeps going. He finds other simple ratios, 2 to 3, 3 to 4, that also produce pleasing harmonies. He's doing mathematics. Pure abstract ratio mathematics. He doesn't know anything about sound waves or frequency or vibration physics. He's just playing. Fast forward 2,000 years. Physicists studying how sound actually works, the physical mechanics of vibration, discover that the exact mathematical ratios this musician found are the precise description of wave harmonics. The musician wasn't predicting physics. He was just following mathematical patterns because they were elegant. And somehow the physics was already there, waiting inside the math. Now multiply that coincidence by 10,000 across every field of physics over the course of several centuries. That's Wigner's point. But here's where it gets interesting. This isn't just ancient history. The most shocking examples come from modern physics, where mathematicians developed abstract structures for no reason other than that they were beautiful or logically interesting. And then physicists, decades later, desperately needed exactly those structures to describe something real. The beautiful accident of curved space. In the early 1800s, a mathematician named Bernhard Riemann sat down and asked himself a purely hypothetical question. What would geometry look like if space wasn't flat? Flat geometry, the kind you learned in school, works perfectly on a flat piece of paper. Parallel lines stay parallel forever. The angles of a triangle always add up to exactly 180 degrees. Pythagoras' theorem holds everywhere, always. But Riemann wondered, what if space could curve? What would the rules of geometry look like then? He had no application in mind. No physical theory he was trying to build. He was exploring mathematics the way a sculptor explores a block of marble, following the form wherever it wanted to go. He developed what became known as Riemannian geometry, a rich, complex, beautiful mathematical framework for describing curved spaces of any number of dimensions. It was considered interesting but abstract, useful for mathematicians, largely irrelevant to physics. Then, about 60 years later, a young patent clerk named Albert Einstein started thinking about gravity. Einstein had a radical idea. What if gravity isn't a force at all? What if massive objects actually bend the fabric of space and time? And what we call gravity is just other objects following the curves in that bent space. What if the Earth doesn't pull the moon, but instead the Earth curves space around it and the moon is just rolling along that curve? It was a breathtaking physical intuition, but to turn it into actual equations, to make predictions, to test the theory, Einstein needed mathematics. And specifically, he needed mathematics for describing curved space. He needed Riemannian geometry. Exactly, precisely, completely. The mathematical framework that Riemann had developed for no physical reason whatsoever 60 years earlier. Stop. Think about that for a moment. A mathematician explores a purely hypothetical question about curved space. He develops an entire mathematical framework. 60 years pass. A physicist working on an entirely different problem, a physical problem about gravity, discovers that this abstract mathematical structure is exactly what he needs, not approximately, not after modification. Exactly. Feynman would say, "I find that very peculiar," and he'd be right to. The universe isn't using calculators now. You might be thinking, okay, fine, math describes physics well, but maybe that's just because math is flexible enough to describe anything. Maybe we're just good at finding the right equation after the fact and calling it a prediction. That's a fair objection. It's worth taking seriously. But here's what makes it harder to hold on to. In many of the most spectacular cases, the math didn't just fit the physics we already knew. The math predicted physics we hadn't discovered yet. The equations pointed at reality before anyone looked there. Consider the story of antimatter. In 1928, Paul Dirac was trying to reconcile two of the great theories of his time, quantum mechanics and special relativity. He wrote down an equation, a beautiful equation by his own description, that correctly described the behavior of electrons. It was a triumph. But the equation had a strange property. It had two solutions, not one, two. And the second solution described a particle identical to the electron in every way. Same mass, same properties, except with opposite electric charge. Nobody had ever seen such a particle. There was no experimental evidence for it, no physical reason to expect it, but the math demanded it. The equation wouldn't work with just electrons. It required the existence of an opposite. Dirac followed the math. He predicted the existence of what he called an anti-electron, what we now call a positron, the electron's antimatter twin. 4 years later, in 1932, Carl Anderson discovered the positron in cosmic ray experiments. The math had been right all along. Dirac hadn't looked at the universe and described what he saw. He had followed mathematical beauty into unknown territory, and the universe was already there, waiting for him. This happens again and again. The equations of general relativity predicted that the universe must be either expanding or contracting. Einstein was so disturbed by this that he added a fudge factor to make it static, a decision he later called his greatest blunder. When Edwin Hubble actually looked at the sky and saw galaxies rushing away from each other, the math had already known. The mathematics of quantum field theory predicted the existence of the Higgs boson 50 years before the Large Hadron Collider finally detected it in 2012. The equation said it had to be there. And it was. Is mathematics discovered or invented? This is the question lurking beneath everything we've been discussing, and it's one of the oldest questions in the philosophy of mathematics. On one side, you have mathematical Platonists. They argue that mathematical truths exist independently of human minds. The circle ratio we call pi 3.14159 and on forever without pattern was true before humans existed. It will be true after we're gone. It's true on other planets where nobody has ever held a pencil. Mathematicians don't invent these truths. They discover them, the way an explorer discovers a mountain that was always there. On the other side, you have those who argue that mathematics is a human construction. We invented the rules, the axioms, the definitions, the logical framework, and everything else follows from those invented starting points. Pi isn't discovered. It's a consequence of definitions we chose. Change the definitions, get different mathematics. Both positions have serious problems. If mathematics is purely a human invention, why does it describe physical reality? Why would our mental constructions match the behavior of electrons and galaxies? That's an extraordinary coincidence that the invention view struggles to explain. But if mathematics is a timeless, mind-independent reality, where exactly does it exist? In what sense are abstract objects like numbers real? What does it mean to say that pi exists somewhere, floating in space, waiting to be discovered? Now here's where Feynman becomes genuinely useful, because Feynman had a characteristically skeptical, pragmatic response to this entire debate. He thought the question of whether math is discovered or invented was perhaps the wrong question entirely, or at least a question we shouldn't pretend to have answered. He was deeply wary of philosophical positions that sounded deep but couldn't be tested. He would say something like, "I don't know what mathematics is in some ultimate philosophical sense, but I know what it does. And what it does is extraordinary." This isn't avoiding the question, it's a specific philosophical position. Be cautious about metaphysical claims you can't verify. Keep your attention on what you can actually examine. Feynman's pragmatic view was that mathematics is an incredibly powerful tool for noticing and expressing patterns. The universe has patterns, deep, consistent, interconnected patterns. Mathematics is the language we've developed, or discovered, or some of both, that is precise enough to capture those patterns. But he wouldn't go further than that. He wouldn't say the universe is mathematics in some deep metaphysical sense. He wouldn't claim that mathematical Platonism is true, even though the evidence sometimes nudges in that direction. He kept his sense of wonder alive by keeping the mystery genuinely open. Mathematical beauty as a guide to truth. Here's something strange that physicists have noticed, and mostly try not to talk about too much at scientific conferences, because it sounds vaguely mystical. Beautiful equations tend to be correct ones. Not always. Not as a rule you can rely on blindly, but with a frequency that's more than coincidence. Dirac famously said that it is more important for a physical equation to be beautiful than to agree with experiment. Now, he didn't mean we should ignore experimental evidence. That would be absurd. What he meant was something subtler. In the early stages of theoretical physics, when you're groping toward a new theory without much data to guide you, mathematical beauty, elegance, symmetry, simplicity seems to be a reliable compass pointing toward truth. General relativity is beautiful. In a way that goes beyond aesthetics, it has a deep, inevitable coherence. Every part fits with every other part. There are no ugly patches or arbitrary constants that had to be inserted by hand. When you see it whole, it has the feeling of something that couldn't have been otherwise. The standard model of particle physics, which describes all known fundamental particles and forces except gravity, is also beautiful. In a more complex way, the way a fugue by Bach is beautiful. There's an underlying mathematical symmetry structure called gauge symmetry that gives the whole thing a kind of logical necessity. And quantum mechanics, despite being famously weird and counterintuitive at the level of physical interpretation, is mathematically clean and precise in a way that demands respect. Feynman noticed this pattern and was honest about it. He acknowledged that physicists often use aesthetic judgment as a guide when the data alone isn't enough. But he was also careful to warn against taking this too far. Beauty is a heuristic, a helpful rule of thumb, not a guarantee. The universe doesn't owe us elegance. There have been theories that were mathematically gorgeous and experimentally wrong. There have been theories that seemed ugly and asymmetric that turned out to be exactly right. Physics is ultimately empirical. The experiment has the final word. But the fact that beauty and truth correlate as often as they do, that's another layer of the mystery. What it feels like to think in equations. Let's do a thought experiment about what's actually happening when a physicist uses mathematics to understand the world. Imagine you're Feynman. You're sitting at your desk and you're trying to understand how electrons interact with light. Not roughly, not approximately, exactly, in a way that makes precise, testable predictions. You don't have a direct visual. You can't watch an electron with your eyes. It's too small, too fast, too fundamentally quantum to behave like a tiny billiard ball you could just track with a camera. So what do you have? You have mathematics. You have a framework, quantum electrodynamics, that lets you assign mathematical objects to physical things, states, operators, amplitudes, and you follow the mathematics. You calculate using the rules of the mathematical framework, and you get a number. Then you go to the laboratory. You run the experiment. You measure a quantity, the magnetic moment of the electron, say how strongly it behaves like a tiny magnet, and the number from your calculation matches the measured value to 10 decimal places. 10 decimal places. That level of agreement between a mathematical prediction and a physical measurement is the most precise in all of science. It's like predicting the distance from New York to Los Angeles and being accurate within the width of a human hair. Now ask yourself, what just happened? A human being sat in a room, manipulated abstract symbols according to mathematical rules, produced a number, and reality agreed with that number to extraordinary precision. Is the mathematics describing reality? Or is it somehow participating in reality? Is the universe following mathematical laws in some deep sense? Or are we just very cleverly projecting mathematical patterns onto a reality that doesn't actually care about our equations? Feynman didn't know, and he thought that was wonderful. The patterns that were always theirs. Here's a different way to think about the mystery. One that might feel less philosophically vertiginous while still doing justice to the strangeness. Maybe the universe doesn't obey mathematics in the sense of following rules. Maybe the universe just is a certain way. It has regularities. Deep, consistent regularities. The same physics operates here as on the other side of the galaxy. The laws don't change from Tuesday to Friday. If you do the same experiment twice under the same conditions, you get the same result. Mathematics is the human tool we've developed to describe regularities precisely. So the fact that mathematics describes physical regularities isn't so strange. Mathematics was specifically evolved over thousands of years of human effort to be good at exactly that job. On this view, we don't need to be mystified that math describes physics. Math is, roughly speaking, the study of patterns and their consequences. Physics is, roughly speaking, the study of the patterns in physical reality. Of course, they connect. They're both in the business of patterns. But this doesn't fully dissolve the mystery, because it doesn't explain why physical reality has such deep, consistent, mathematically precise regularities in the first place. It doesn't explain why nature is lawful rather than chaotic. It doesn't explain why the same equations that describe electrons here also describe electrons in a galaxy 12 billion light-years away. It doesn't explain why there are patterns to describe. And that question, why is there order rather than chaos? Why is the universe the kind of place that can be understood at all? Is one that physics alone may never be able to answer. Feynman was comfortable with that. He thought the inability to answer a question wasn't a failure. It was an invitation, an open door, the deepest gift. There's something Feynman said that has stayed with people long after they heard it. He was talking about why he loved science, why he loved the particular activity of trying to understand the world through physics, and he said something like this: "When you look at a flower, you can enjoy it as a work of beauty. But a scientist can also see the miracle of molecular machinery inside it, the structure of proteins, the flow of energy, the elegant chemical reactions that produce the color and the scent. And that knowledge doesn't diminish the beauty. It adds to it. It opens layers upon layers of beauty that the purely aesthetic view can't access. That's what mathematics does with physical reality. When you look at the night sky without mathematics, you see stars. Beautiful, yes. Ancient, yes, but mute. When you look at the night sky through the lens of mathematics, the stars start speaking. The way light shifts in frequency tells you the star is moving and how fast. The spectrum of colors tells you what elements are burning inside it. The pulsation rate of certain stars tells you their actual brightness, which tells you their distance, which tells you the scale of the galaxy. The mathematics doesn't replace the beauty of the night sky. It amplifies it. It reveals depths that bare eyes can't reach. And this, Feynman would say, is the real gift. Not the practical applications of mathematics and physics, though those are genuinely extraordinary. Not the philosophical conclusion about whether mathematics is invented or discovered, though that question is worth sitting with. The real gift is what Feynman called the pleasure of finding things out, the particular joy of discovering that the universe makes sense, that it has structure, that it has depth, that it rewards understanding. The fact that mathematics works, the fact that abstract symbols can describe reality with such precision, means that the universe is comprehensible. It means that human minds, evolved on a small planet around an ordinary star, can nevertheless reach out with pencil and paper and touch the behavior of quarks and the curve of space-time and the expansion of the cosmos. That is extraordinary. That might even be the most extraordinary fact there is. A mystery worth keeping. Wigner called it unreasonable effectiveness. Dirac called it mathematical beauty. Einstein called it the most incomprehensible thing about the universe, that it is comprehensible. Feynman typically had a simpler way of putting it. He said the universe is not only queerer than we suppose, but queerer than we can suppose. And he meant that as a compliment. The universe's refusal to be fully pinned down, its tendency to exceed every framework we build for it, is the reason there's always more to discover. We don't know, in any final sense, why mathematics describes physical reality. We have partial answers, philosophical frameworks, suggestive observations. But the deep question, why abstract human thought and physical reality should fit together at all, remains genuinely open. And perhaps it should, because a universe that revealed all its secrets at once would be a universe not worth living in. The mystery is part of the gift. The open question is what keeps us reaching. Mathematics is humanity's telescope into the structure of the universe. We built it. We use it. We're astonished every time when it works. And somewhere you can almost hear Feynman laughing, that characteristic laugh of his, half delight and half disbelief at the sheer absurdity and wonder of the whole thing. The universe speaks mathematics. We still don't know why, and isn't that something?